So, India's cities are just growing upwards, right? Skyscrapers and high rises are popping up everywhere. But what happens when the ground beneath them starts to shake? Today, we're digging into a really critical issue. How do we make sure our towering concrete buildings can actually stand strong when a major earthquake hits?
So let me ask you a question, a really direct one. That building you live or work in, have you ever stopped to wonder if it's truly ready for the big one? It's a question we should all be asking.
And that question, well, it leads us to a pretty startling reality. Think about cities like Guwahati. It's located in India's highest seismic risk zone, and it's seen this massive boom in high-rise construction. But here's the kicker. The vast majority of these modern buildings have never actually experienced the powerful shaking of a major earthquake. They are, in a very real sense, a ticking time bomb.
Yeah, so how did we even get into this situation? Well, for decades, construction was moving way faster than safety standards could keep up. Most buildings put up before the 90s, they honestly weren't really designed with earthquakes in mind. And then came 2001, the Bhuj earthquake. That was a tragic wake-up call that exposed just how deep these vulnerabilities were, and it led to much, much stronger codes. The problem is that huge stock of older, weaker buildings is still standing.
And one of the most common and frankly dangerous flaws in many of these buildings is the soft story. And you know exactly what this looks like. It's that ground floor, right? Wide open spaces for parking or shops, all held up by just a few slender columns. During an earthquake, that floor wobbles like jelly compared to the stiff, walled floors above it, creating a critical weak point that can lead to total collapse. Okay, so we've identified the problem, a big problem, but thankfully, we also have solutions. And it all kicks off with what you could call a health check for the building, a thorough diagnosis to figure out exactly where the weak points are. Right, so how do engineers actually do this diagnosis? It's not just guesswork, right? Nope. There's a very systematic methodology they follow, and it's all laid out in India's own national guidelines. Okay, so take a look at this. This is the official flowchart from the Indian Standard Code, IS 15988. You can think of it like a roadmap for engineers. They start with a preliminary evaluation, kind of like an initial screening for obvious flaws, like those soft stories we just talked about. If the building fails that quick check, it moves on to a much more in-depth, detailed evaluation. Now, in that detailed evaluation, engineers calculate a super important number called the demand capacity ratio, or DCR. It's a simple concept, but incredibly powerful. Demand is the force from a potential earthquake that the building is expected to face. Capacity is the building's actual, as-built strength. If the demand is greater than the capacity, giving a DCR over 1, well, that means the building is officially in trouble and needs intervention. All right, so the diagnosis is in. The building's vulnerable. Now what? Well, now it's time for the treatment plan. And engineers have a whole toolkit of powerful strategies, known as seismic retrofitting, to make the structures safer. These generally fall into two main categories. Let's break it down like this. A global strategy is like giving the building a whole new, stronger skeleton to improve its overall resilience. A local strategy, on the other hand, is more like targeted surgery. It's about fixing individual weak points, like a single column that the diagnosis found was at risk. So let's dive into the global approach first. One of the most effective strategies out there is adding something called shear walls. So what in the world is a shear wall? Well, you can basically think of it as a very, very strong, specially engineered, reinforced concrete wall. Its entire job is to resist those dangerous side-to-side forces from an earthquake, and it adds a ton of strength and stiffness to the whole building. It is a total game changer for strengthening an existing structure. And here you can see that whole process, from the blueprint to the actual build. On the left is the engineering diagram from the Indian Standard Code showing how a new shear wall is meticulously designed. And on the right, you see that plan in action. A crew is literally constructing that exact wall, adding a tangible backbone of strength and safety to the building. Okay, so that's the big picture, global approach. But what about that local, surgical level? Well, one of the most common and critical techniques is something called reinforced concrete jacketing, and this targets the building's most vital supports, the columns. The whole thing starts with some pretty tough prep work. As you can see in this photo, workers are deliberately chipping and roughening the surface of the original column. Now, this isn't damage, it's a super important first step that creates a rugged texture to ensure a powerful, permanent bond with the new concrete that's coming next.
Next up is the steel. This diagram shows you the heart of the technique. A new, robust cage of steel reinforcement is built around the original column. This new skeleton is then encased in fresh concrete, creating a jacket that dramatically increases the column's strength and its ability to flex without breaking. So, to quickly recap that jacketing process, it's a clear four-step sequence. First, you roughen the old column. Second, add that new steel cage. Third, inject a powerful epoxy bonding agent so the old and new concrete act as one solid piece. And finally, you pour the new, high-strength concrete to form the jacket. And that thickness isn't just a suggestion. The whole process is governed by strict codes. The Indian standard IS 15988 specifies that the minimum thickness for one of these jackets must be 100 millimeters, about 4 inches, to ensure you get a substantial and effective layer of new strength. So we've seen the diagnosis and the treatment, but what's the outcome here? These engineering methods aren't just technical exercises, they are practical, proven steps toward a much bigger, much more important goal: building a safer tomorrow for our cities. So what's the big takeaway? Why does all this matter so much? First and foremost, it saves lives, period. It also preserves the homes and infrastructure we already have, which is way smarter and cheaper than rebuilding from rubble. All these methods are guided by robust Indian codes, upgrading older buildings to modern safety standards. This is, quite simply, a vital and proactive investment in our city's resilience. And hey, you don't have to take my word for it. This quote from our source material says it all. India's current building codes have been tested in real earthquakes and have been proven effective. Choosing to ignore them is, and I'm quoting here, a sure recipe for distress in future. Can't get much clearer than that. Our skylines are a symbol of our ambition. But as we continue to reach for the sky, we have to ask ourselves, are we also ensuring our foundations are strong enough to stand their ground when things get rough? The real question is, are we doing enough?